Hello and welcome back to Calculus 1, section 3.2, working with derivatives. Working with derivatives, not too happy with the title, but maybe would be better the graphical representation and connections between the function and the derivative. So last time we talked about derivatives. We defined the derivative f prime of x as the limit h goes to 0 of f of x plus h minus f of x divided by h, and then we spent some time working this out, and at the end we get this derivative function. So this over here is the derivative function. Now we said that's the derivative function computes all possible slopes. Of f of x. So that's the main idea of the derivative. That's what it is. It computes all of the slopes. So what that means is that it measures the change of the function at every point. So now the meaning of this statement here, right? The meaning of this statement is the derivative measures the change. I should say the instantaneous change, but we'll insert that word later. So derivative measures the change at each point of the domain. Of f of x. So now we are clear that you have a function f of x and you have its derivative, which is also a function, but it's a different function. I believe you were supposed to compute on your exam one of these functions, right? So using the limit. So pretty much the same stuff we did in class. You look at the difference in a difference quotient, you apply the limit. So let's say you have f of x equal x squared, and I'm just going to say insert work here, because you're supposed to know how to do this, and at the end it spits out 2x, right? So now clearly a different function. The one on top is a parabola going through 0, 0, right? And the one on the bottom is a linear function going through 0, 0. It's not a 45-degree line because y equals x is 45. So now look, on this one I put y, so the top one is xy graph. The bottom one is xy prime graph, because the line that you have, the graph, is the derivative graph. It's not the function graph. Well, derivative is a function, but you know what I'm saying. So what I want to do now is I want to establish a connection between the graphs of the function and the graphs of the derivatives, and see some cases and situations where looking at the graph of derivative so some situations where looking at the derivative graph you gain information faster than looking at the actual function graph. So let's go and do this in stages. The first graph I want to consider is the graph of the constant function. Say this is going through 3, so y equals 3 or f of x equals 3, whatever you want to call it. It's the same thing. So this is your original f of x, right? What is the derivative of this function, right? And then what would be its graph? And we're going to do all of the graphs in red for derivative and in black for the original function. So 2 colors, everyone. I'm very happy that you all travel with multiple colors, and you can do this in your notes 100% of the time. Oh, by the way, the notes are available in Google Docs. I switched to the Google Docs folder because of the impending doom with our file repository. So each video that I have that I produced in the last week has the link in the description, and you can obtain notes for your Calc 1 class, the other Calc 1 class, Calc 3, and Stats. So all of the classes that I'm teaching. Your labs, syllabus, and everything else will also be there in that folder. So you have to obtain your course materials. Lions Den is supposed to die in about 2 to 3 weeks. And that's the reason why I switched. So just go there and get the stuff. It's all PDFs, right? All right, so going back to the problem, we have the constant function. Now, I want to draw the derivative. Great, we can do that easily here. What is the purpose of the derivative? What does it do? Measures. I said it differently earlier. Measures what? Derivatives measure change. Derivative measure change. Here. The word change, right there. Derivatives measure change. What's the change in a constant function? Yes, please, use your common sense 100% of the time. Use it until we get to the situation where we divide 0 by 0. In that case, common sense gets retired, but because in some cases we are going to get a half or a 3/4. But in this case, you go, I learned from theory that derivatives measures change. I have a constant function. Constant functions do not change, therefore derivative must be 0, because if you are measuring change and there is no change, answer is 0, right? Look at this, no cake, 0 cakes, right? Right, so the same idea, it's a constant function, so there we go. This over here is the derivative of x. And in this case, easy to say, just equals to 0, and we move on with our lives. So that's the logic behind the whole situation. Derivative of a constant function is a 0. That means that anytime you take the derivative of a constant, like derivative of pi, derivative of 3, derivative of negative 100, they're all zeros, because they are all constants, and constants do not change. So measurement of change is 0. Derivative is 0. Now we move to a little spicier example, where we are going to consider, say, let's go with, I don't know, 45 degrees from -4 to -1, and then go forward, and then double down. So this is at 3, this is at 5. This is your f of x. It is clearly a piecewise function, and we could write the formula for this function, but we just don't care, all right? Because we really don't need it to compute to draw the derivative. What is the change between a -4 and -1? We have interval from -4 to -1. What is the change there? 1. You see that, you know that the change, let me write this in blood. Change is the slope. This desk is flat. If I'm to walk on this desk, the floor is flat. If I'm going to walk on the floor, I'm not going to change the height at which I am because it's flat, right? But if I'm going uphill, or downhill, I am definitely changing the height. So, and uphill, downhill, it's a slope, right? So change is slope, and slope is rise over run. So you can see here that you go 1 unit up, which is rise, 1 unit across, which is run. 1 divided by 1 is 1. Therefore, the change on the interval -4 to -1 is 1 everywhere. So I get to draw this line like this, which is all of the slopes. See, no matter where you pick the point on this line segment, slope is everywhere exactly 1. So, because the slope is +1 everywhere from -4 to -1, I just draw that line. Now, what is the change on the interval -1 to +3? 0. There is no change because it's a horizontal flat. That's the upper example, technically. So I'm going to draw my derivative on x-axis. What is the change, the slope, all of the slopes, from 3 to 5? All I heard is, I need the full voice, like you had breakfast five minutes ago. -2, very good. Observe that the height is at -4. The bottom part is at 0. So you have -4 to fall down, right? From this point you fall down -4 units and you run 2. So yeah, -2. This is -2 right here. So you see that for this particular f of x, we have a step function as our derivative. And something interesting is happening. It's maybe you remember it from your class prep, I'm not sure, but can you see a connection? I say it might be too early, too premature to do that unless you read it, you know. But can you see the connection between the black and the red? Like a rule that is going to be there all the time. If the black line does so and so, red line will do so and so. If the black line does so and so, red line will do so and so. Beautiful. Yes. If the black line has a positive slope, i.e. increasing, to have a positive slope, you have to be going up the hill, right? Losing weight, positive. And then if you are walking on a straight surface, no change. That doesn't count. And if you are skiing or snowboarding down the slope or skateboarding or doing whatever and breaking your bones, that's the negative, right? So you have the negative derivative. So here we go. Positive slope increase, positive derivative. Positive derivative, positive slope is the same concept, different words. All right? Zero slope, no change, zero derivative. Decrease and negative slope, negative derivative. So they all go in the same bag, right? There are 3 different bags, and all of the concepts go in those 3 bags. So if f of x is increasing, that means, if f of x is increasing, that means positive slope, which is equal to f of x prime derivative is bigger than 0, so you draw above x-axis. Next one. If f of x is constant, then we have 0 slope, and that's f of x prime equals 0, and then if f of x is decreasing, we have negative slope and that is equal to the negative derivative you draw below x-axis. And now you look at this, right, conclusion here, which I am going to put in this overrated box, but we have to. We are going to come back to this in at least 2 or 3 different lectures throughout the semester, but this is the essence of what you are learning. So if the function is growing, doesn't have to grow linearly, any kind of growth, exponential, quadratic, cubic, logarithmic, square root is also an increasing function. So whatever kind of increasing function you might have, or a piece of that function that is, you are going to have slope that you draw above x-axis. Constants are always 0, and decreasing is always the negative, and that's it. So now we're going to curve this a little bit to get the more interesting examples on the page. So I'm going to start like this, curve down, go back up, and then end up flat. So this is my, again, black function, f of x, right? Red function, the derivative function. I am going to label this as y, but it's also at the same time y prime, because I will be graphing the red one on the same graph. Cool. Where do we begin? Well, we are going to start by first noticing the change from increase to decrease and decrease to increase. And that happens where? Change from increase to decrease and decrease to increase. Where would that happen on the graph? At? Yes, what do we call that? Vertex. That's only for parabola. What do we call those points? Max and min, thank you. So the max point on top over here, is going to be a change from positive slopes, which are to the left, to negative slopes, which are to the right. So that means that at that point, the derivative has to cut through 0. Also, please notice that the tangent line will have a 0 slope at max and a min. It must. It must have a 0 slope. M equals 0. Anywhere before the max, right, to the left of the max, all of the slopes, as you can see, are negative, right? You draw the little line segments, they're all negative. So I start working on this function by first hunting down all of the all of the 0 slopes. 0 slope occurs at every max, every min, and all constant parts. So I can also go here and say it goes like this, right? So far I have two points and the 0 portion, because that was flat on the other end. And now I need to fill in the rest. So what do we know? We know that the slope is positive, because the function is increasing. So I need to draw that slope above x-axis, like this. Now you might say, well, is it that way or this way? I don't know. I don't have exact functions to work this out. It's a sketch, right? So which way? Some of you might curve it this way, some of you this way. Whatever you master is okay. I just need to see that piece of the line is above x-axis because your slopes are positive on the black line, and therefore red line has to have positive values on its y. The next piece between max and a min is a decreasing piece. You get to ski down this slope. Well, that piece better be below x-axis because it's negative slopes and negative numbers are below x-axis. And then you have another increase, right, over here, which will be a bump above. I'm going to erase this and explain it again. If you missed it the first time, you better catch it now. The part to the left of the maximum point, this is your max over here, and this is your min. So the part to the left of max is increasing, therefore the derivative needs to be that. And then we have decreasing part, which means that the derivative is decreasing. Again, I don't know if it goes like this or like that. I don't have exact functions, so draw whatever. It's a sketch. And then the increasing part over here, the increasing part between the minimum and the constant part is increasing, right? So we have above x-axis. And this red line is f prime of x. Now, there are also, for those of you who want to go advanced and really understand what the hell is going on here, I'm going to say this, so if it registers, awesome. Red line is collection of all slopes. So y values of red line are numerical values of slope. Y values of the red line are slopes, m's, of the black line. So I'm going to pick two values, two x values. That was terrible. Better. I'm going to pick two x values on this in this graph. And now, is this good? No, I don't like it. Better. I don't want it to go through the zero black over here. All right. Note that these blue lines which I drew cut through black and red, right? And I'm going to have a blue 1 and a blue 2. I'm actually going to erase all of this blue stuff. I'll keep the blue sentence, but I'm going to erase the blue on drawing. So I'm explaining a concept much further than what we... So look at this. Do you agree that it's much harder, we're looking at B1, it's much harder to climb the hill at B1 than at B2? Do we all agree that the B2 is somewhat flatter than B1? You see over here at B1, when it crosses the black line, it's really steep, right? Like Spider-Man has no problems there also, but that's out of our realm. So it's very difficult to go up the black line at B1 intersection. And it's quite easy to go up the black line at B2 intersection with the black line, right? It's very easy to go there. Now observe what's happening with the numerical values of y for the red line at those intersections. Hard to climb up, means large change means high y value for derivative. Easy gradual walk up the black line has a low y value of the red line. Red line measures the change. So the more it changes, the more the black line changes, the steeper it is, the bigger number you have as a derivative. So at B1, if the derivative is 20, then at B2 the derivative is 3. Right? Something along those lines. So the steeper it is, the derivative has higher value. Now this means that if you come up to a vertical line, your derivative is infinite. Right? Derivative is infinite. Can climb up that, right? So that's the connection, and we see that the derivatives really tell us very easy on what's what. So I'm just going to erase this B1 and B2 so they're not confusing for your later reference. But come on, pen. Pen, wake up. There we go. Hello, pen. Good. The next situation, I'll write the sentence first. Derivatives preserve locations of vertical asymptotes. The cheapest graph that we can consider in this case would be f of x equals 1 over x. It has the vertical asymptote at x equals 0, y-axis, right? So f of x equals 1 over x. And you draw the function. Now you draw because you memorized this one. You better know it. So this is your standard 1 over x. It has the vertical asymptote at x equals 0. Now I need to draw my derivative. All right. To draw my derivative, I note that both pieces of this function are decreasing. And the derivative maintains the vertical asymptote at the same spot. Decreasing function means your derivative lines must be below x-axis, and because both parts are decreasing, both derivative lines must be below x-axis, and they must follow vertical asymptote. I have to invoke common sense on that one. If everything you draw that has to be below x-axis and everything you draw has to follow the vertical asymptote, what is the only way that you can draw these pieces? Right? That's it. There's nothing else that you can draw. Again, the decrease of both black lines, the decrease. If you are walking on these pieces, you are always going downwards. The decrease commands to be below x-axis. The sentence above tells you that the vertical asymptote must be preserved. There is no other way to draw the derivative other than those two pieces. So, what is the derivative graph? The derivative graph will simply be this piece and this piece. So now it's a little bit confusing that black and red over there coincide. They're not exactly the same curve. I will tell you what the derivative is. We are going to actually learn how to do this today. The derivative is -1 over x squared. That's what the derivative is. If you are to go to your procedure, right, the limit f of x plus h minus f of x over h, as h goes to 0, and you crank this function, which we probably did, you will get -1 over x squared. Did we do that one? I click and it's right there. Nice. So here it is. Function is f of x. Here's the entire procedure. You just need to go to notes 3.1. Last example is exactly that. Great. So we see that the derivative of 1 over x is -1 over x squared. Now, we know, because we are mathematicians over here, that's the derivative for 1 over x. And so that's the graph for 1 over x. And this is the graph for 1 over x squared. But we have this negative. And the negative flips on x-axis, right? So it's going to look like this for -1 over x squared. You see how everything clicks in, the shifting the function, reflecting the functions, and all of that stuff with all of the other things. So now you actually see that we use the basic knowledge from pre-calc 1 of what 1 over x squared looks like, and we use the reflection also from pre-calc 1 to create the graph for something that we computed. Now, on the other hand, when we did the working with derivatives, I used a completely different argument to obtain the same thing. I said function is decreasing everywhere, so all of the pieces have to be below x-axis, and then vertical asymptote has to be preserved. And as I had before, right, you have to follow that division that these two are prohibited regions because there is no increase anywhere, and you have to follow the two red lines as guides. In this case, x-axis because decrease, and y-axis because it's the vertical asymptote. Now, your book will have some spicier examples that encompass all of these individual examples into a single graph. So your homework, and obviously later on your exams and so on, if you pick to have them, will have you look into the, let's say, graph like this. So we're going to put, say, let's put the vertical asymptote at -2. Let's go from, let's do this, and then go here, bump, and go flat. So try to now combine all of your, so black one is f of x, right? Try to combine all of the knowledge that you accumulated so far to get this. Try to draw the derivative. This type of problems that your textbook has is homework, and generally this is what you check, because this has everything on it. Please remember, you preserve vertical asymptote. All min and maxes give you the points through which the graph will go on x-axis, right? So keep that in mind. Min max, you start there. Min max flat part. All right, let's take a look. So we are going to preserve the vertical asymptote. We are going to locate the min and place the x-intercept at that x value, and the max with another intercept. We are going to go where the flat part starts and draw 0 derivatives because the slope is 0 at that part. I am going to look at this increasing function and draw the derivative. Since the function is increasing, I am allowed to draw only above x-axis. So I will go with the sluggish increase to the rapid increase, because that's what's happening with our line. So I draw the derivative there exclusively above x-axis because the whole piece is increasing. The black line is increasing, red line has to be confined above x-axis. Going to the other part, the function is decreasing, which means I have to be below. And then the function is increasing, I have to be above. And the function is decreasing, I have to be below. And the red one is the derivative. Does it make sense? Great. Let's go and do 3.3.